Hey everybody, this is Dr. B, and we're going to have some fun with DuckDB today, particularly the fast top-end aggregation and filtering by a group with DuckDB. This was a wonderful article by Alex Monahan that came out late last year, where he goes through the process of explaining and illustrating what this is exactly. So this is most familiar to a partition SQL query, where you might partition or group along a certain field and then sort and rank by another field within that group. So that's the top end. Let's say top 10 movies of comedy in 2024. You'd have two groups there. You'd have the genre comedy and the year 2024, and the N for the top end would be top 10. So we're going to do this in a geospatial context, and we're going to find the max draft for AIS shipping traffic vessels in spatial bins. And we're also going to do this with LiDAR data, where we're going to use this same query to supersede LiDAR classification into a digital elevation model that we're going to create using PDAL. And all of this is going to happen within Python. And so there are a couple of Easter eggs in there that I'll highlight as we go. So just a quick overview of the data sets involved here. The USGS 3D elevation program LiDAR data is publicly available, and there are at present more than 70 trillion data points in there. And those are raw LiDAR. Well, not necessarily raw. They are potentially raw, potentially classified, processed. So more on that, you'll have to go check out USGS. Here's an example for New York City. Just to give you an idea, these are point-based. If we were to go into those, you'll see that it will resample its resolution. Quite a data set. So that is a familiar LiDAR data set here. You can see the city emerging. And then for the AIS data, we'll be using data from marinecadastre.gov. And so if we look at the point summary throughout the years, this is a big data set. But since 2018, the schema has been fixed. And within that schema, they've been outputting a file for all shipping traffic for all U.S. territories per day. And they've been putting that out as a compressed CSV format. So for any given day, we've got a file. That's why we have about the number of days in a year is the number of files in a year. Now, this stops at 2023, but for 2024, there are data posted. And if we scroll to the bottom, we'll see that the data go up to late September. So not a full year there for 2024, but it'll be there by the end of the first quarter of 2025. The way their schedule is they lag it by 1 quarter. So we can expect it in the spring. What's in that data? We have 17 fields, so we have a lot of attributes that we could use. Some of them are specific to the vessels that are in there, and some of them can be used for aggregations. So in this case, we're going to be finding the maximum draft for a given spatial bin, and we're going to have to provide that spatial bin. It's not provided for us here. So this is basically unstructured data. Whereas in the USGS, the data can be queried based on an octree structure. It can be, you can pull out subsets of the data pretty easily. In this case, we're going to have to massage the data so that we can query it spatially. We're going to be pulling in both cases, the USGS and the AIS data cases. We're going to be pulling the data direct from URL, and we're going to be multi-processing at times and multi-threading at times. And now you could do that with other packages in Python. So if you wanted to multi-thread pandas, for example, you could use daft or dask. But we want to use DuckDB for this. And with respect to DuckDB, you could use IBIS, which can run DuckDB's engine on the back end. Now, IBIS will use DuckDB's relational API so that those of you who are not familiar with the SQL language can stay in a Python syntax for issuing these queries. I'm natively a database fan and I'm very familiar with it, so I prefer to stay in SQL when I'm running SQL queries, and I prefer to stay in Python when I'm dealing with Python natives, such as in Pandas. Now, the drawback here is that Pandas is natively single-threaded without the help of those additional packages. And Python, even with those packages, still has a global interpreter lock, which is notoriously known for keeping things single-threaded. DuckDB is a wonderful tool in the sense that it is somewhat immune to that global interpreter lock. So DuckDB can use as many threads or CPU cores as it needs based on a user setting, which is a fantastic option. So the takeaway point here is that Python can leverage DuckDB for CPU bound or IO bound processes. So this, supports all of the in-memory and larger than memory scenarios that you might encounter. You can just use DuckDB and Pandas, for example, and have a really powerful workflow. So the best way to get started in doing that is to set up a function that will prepare your DuckDB connection object for you. So in this case, all of my input arguments are optional because in DuckDB's case, if you don't give it any input arguments, you'll get a stock in-memory database. But we do want to pass it some things. You can control the number of threads that you want DuckDB to be limited to. So if you have 16 cores and you're going to multi-thread in Pandas, you can decide how many of those cores go to Pandas and how many of those cores are going to be dedicated at any given time to DuckDB. Same thing for spillover memory processing. DuckDB is very elegant about trying to manage what happens when it runs out of memory. So at 80% RAM utilization, DuckDB will start to spill over in any number of various ways. Natively, it'll start spilling to disk, which would be a swap space. But you can bypass that, and you can bypass swap, and you could pass it a temp directory, and you can even put a cap on that and say the max temp directory size should not exceed. So if you have a solid state disk lying around or an external SATA, for example, any of these types of things, you can leverage those with DuckDB really easily just by passing the pragma in. Also, in both cases, we are going to be reading directly from URL. So we're going to be streaming the point clouds in the AIS case, we're going to stream them into a pandas data frame. In the USGS LiDAR case, we're going to stream them into PDAL. So PDAL can read the entwined point tile JSON resources pretty easily, and it can do some basic PDAL processing to prepare that data for pandas data frame. So at that point, it'll look a lot like the AIS dataset here, where you can see what we're doing is we're taking a data frame. In this case, we've read the compressed CSV file, and we've overridden the header values and the data types as well, because those AIS CSV files are known to have some typos in the headers, and they also have null values. So you can't always go on the data dictionary that they provide. You have to make sure that it's compatible with your workflow. So we will be reading it in, and then we'll be recasting types into our tables later. But all that aside, the really convenient thing here is that DuckDB allows you to mount or bring a data frame in as a table view. And so it's very easy to do. Once you have a data frame available, then you just register it against your DuckDB connection object. So you give it a name that DuckDB will use internally. So we're going to call our data frame df. Internally, it'll be called AISDF. And so you can see here, that's part of our first query. And this query is a copy to Parquet. You can see the way it opens up. And then we're going to bound a inner query, which is going to do the work. But the important thing to note here is that we're not going into DuckDB tables. We are doing all this on the data frame natively, and we're sending it directly to a Parquet file, and it'll be a GeoParquet on top of that. So the first thing we want to do is assign our spatial index. And so we're going to use Uber's H3 system for that, and we're going to give it the highest level of detail is 15. And then while we're here, we might as well bin the data to these level of detail 15 cells, which are about 1 meter. in area. So we're going to give it a spatial index. We are also going to nest all fields in the table into one so that we can do a fast binary hash. And then we're going to look up the draft values against that. And we're going to take the maximum draft out of that. So this max by is in the article that we started this talk with. Explains what this is doing, but is basically nesting the table into a single column and then doing a max draft lookup against that. And it's grouped by the spatial index. So what's actually going to happen in the larger sense is for any given H15 cell, which there will be millions and billions even, for any given cell, we're going to find the maximum draft for all of the data that occupied that cell. So if we had 1 year's worth of data or 10 years worth of data, the number of points per cell is going to change, but we're always going to take the maximum. And then we're going to also compute a geometry for the point. So the coordinates that are coming in that CSV, the longitude and latitude, we're going to use the cell centroid as the points so that they all get binned to the bin center will be the coordinate that we output. And so last thing to do is group and order that. The more order there is in the Parquet, the more optimized the Parquet will be by any client that uses it, such as QGIS. Skipping down the line a little bit, if we want to re-bin or if we want to take those 1 meter bins and then group them into a lower resolution spatial bin for aggregation or for efficient GeoParquet, for example, we could take the H3 level of detail 15 bin and we could recompute that to something of a lower resolution. Let's say H3 at the level of detail 11 would then take all of those 15 meter bins and then partition them or group them into a larger bin on the order of 45 meters squared in area, so that we can then do things like find the maximum draft within a given meter, and then we could say take that and do it again, but find the maximum draft in a given channel scale, so 45 meters, or we could just use that to group things out. So then we can hive partition the data further down the data pipeline. But this is a secondary query which will allow us to then rebin our AIS data into additional bins for that purpose. So we can then take our time window and vary it. So we'll have these daily files, which we can then rebin into monthly files or yearly files or multi-year files. And we can also change the spatial partitioning for each of those given windows of time. Now, as far as running these queries go, I'm going to show you 3 examples. So we had the 2 queries that we just looked at, but then there's a third implementation here. If we are using a DuckDB database to offload these large points into, we would do that because we don't have the memory or the CPU to manage the whole thing on the fly. Then we would use a DuckDB database. So we would create a table, which I didn't show you that, but that's in here as well. The caveat with DuckDB is it can handle concurrency for reading, but for writing, you're only allowed to have one write going on at a time, so it doesn't do concurrency within the same table. So you're going to need a threading lock for that, and so that's what this third option is here. So if you're using an actual DuckDB database, then you're going to need a lock. Now we can take a look at what's going on there. So we have a sub-function for, here's just creating the tables. It's the AIS dictionary plus the Uber spatial bin. But back to the DuckDB part, we would also want to chunk it. So we'll separate our pandas data frame into chunks and send each chunk to the database. But inside of that, it looks the same as our other process, barring the lock. So we would let's just jump back over there. If we're sending this to a DuckDB database, we're going to do the same thing as far as registering a data frame. We're going to wrap the whole thing in a transaction. That just speeds up the query a bit. we're going to create a temporary table, which is actually going to write the data from the data frame. Same query though, but instead of a copy to Parquet, it's going to write into our database table. Well, it's going to write into our temporary table, and then it's going to select from there and write into our DuckDB table. And then there might be duplicates in there. Then we could honor this on conflict clause. And we could say, if you do encounter a duplicate point, take the one with the maximum draft. So this is in here because this may not happen per file, but it will happen throughout the entire data set. So if you gave it several years of data, you're certainly going to have duplicates on any given H3 bin. But barring that, you can see that the lock is going to come into play right here, right when we're calling that function. And the reason why it's there and not for the whole query is because we can still allow Python to set up, downloading the file into data frame, even processing the data frame to a degree. You can do all that in parallel. It's the actual write that we want to put the lock on, and so that's what we're doing right here. So here we're going to fire that off in parallel. We're going to run 2 Python cores and 7 DuckDB cores. So that should use 14 of our 16 cores for the processing. And we're going to look at the profiler too to see what's going on in the background. And so I'll pull that up after we get started here. But let's go ahead and kick this off. And then we'll bring the other profiler in. And now we can see this blue line in the network panel is the download. That was pretty quick. And then we can see we're immediately starting to increase our memory consumption because now we are writing we're writing from the file to the pandas data frames. And we know that's what's happening because that's happening in a single threaded sense. We can see from the CPUs, we have 2 cores and we can see that no more than 2 are ever really going to spike here as memory grows. Now, when memory grows and all cores are in play, we'll know that we're in a DuckDB space. And so we can see we're transitioning to that right now. And so you can see DuckDB is taken over, and as it runs that query, it's using more memory because it's creating a hash lookup against the whole table. So it really kind of doubled the data for that moment. But you can see that is a really fast process compared to downloading and loading the data into memory. So then we're going to write it out to GeoParquet file. And so you can see that we already have a new download kicked off. And you can also see from the bottom that we've started writing something to disk. So we've gone through a cycle. So we've got 2 files there now, and we got 2 downloads that were kicked off as a result. So we know that we have gone through 2 successful loops in parallel, and now we're doing it again on the next cycle. Real quick, let's take a look and compare the USGS LiDAR pipeline to the AIS pipeline. And we'll start with this entwine point tile to digital elevation mile function, wherein we are going to give it a bounding box to send to the JSON resource. And this will be used as the initial filter. So the initial scrape is done by bounding box, but it's actually done by 3-dimensional bounding box. You can pass it the Z band or the elevation band. And if it wasn't in the native entwined point tile projection, which is pseudo Mercator, you could specify one. So I'm just specifying one to remind me that I can do that. So you can actually give it your bounding box in another projection. Now I'm going to be demming in a geographic coordinate system, so I'm going to give it this funky ratio, which will give me a approximately meter resolution in my output dem cell sizing. Now if I'm doing this in UTM, I would just take off the fraction and I would just go with 1. So the PDAL pipeline, PDAL pipelines are JSON formatted. So in Python space, we can just start those off as dictionaries and then string them together into a JSON dumps. after the fact. So one by one, we can go through these and we can rearrange them if we needed to. Try to keep them in order as best I can. So we're going to kick off the process by invoking the readers.ept, is PDAL's readers function for entwined point tiles. We are going to pass it the URL. We're going to pass it the bounds that we just discussed. And we're going to state the CRS, or the coordinate reference system, that it uses. And then we're going to impose one filter in PDAL space, which is going to eliminate all classifications that are not 2, which is ground, 40, which is a topobathymetric point, 43 would be a submerged object that's not part of the IHO standards, 44 is a submerged object in the S57, I believe, maybe S100 class of objects that would be submerged in a maritime domain. We're also going to filter to our hex cell as a well-known text polygon. This could be any polygon at this point. And then we're going to reproject that to WGS 84. And lastly, for this first stage of the pipeline, we're going to compute the H3 cell ID at the highest resolution of 15. And we'll use that for spatial binning. And we'll do that with our superseding algorithm, which will be taking the highest priority classification for any given H3 ID. And then the last two are going to be used in a second stage PDAL pipeline, wherein we will read what the superseding output is, and we'll write that to dem. So here's the first pipeline, and you can see what we're doing is we're just dumping that string of dictionaries as a JSON. So we've got them, this is our workflow right here, EPT reader, range filter, polygon, mask or crop, reproject, and H3 index. Execute that. It will provide us with a structured NumPy array, which we will then strip out because it's structured. We know the names and data types. And so we can pull those out, dump them into a pandas data frame, send that data frame to our superseding, which looks like this. It's very basic. It looks identical, almost identical, in fact, even shorter than our AIS, wherein we're doing that same fast top-end aggregation. So we're going to pass in those columns, XYZ classification and H3 cell ID. We're going to group it on cell ID, and then within each cell ID, which is basically a square meter, but in a hexagonal sense, we are going to take the maximum classification for that bin. And we're going to send that back to our Python utility as a data frame. And so then it's going to pull that new data frame points, and it's going to pass that back into the second stage PDAL pipeline, which is just going to state that it's in the WGS 84 projection, and then immediately start writing to a digital elevation model. And then just to be clean about things, we're going to optimize that output by calling a subprocess to run the GDAL add overlays so that we have that pyramid structure of thumbnail images. It just makes the GeoTIFF more optimized when browsing with something like QGIS. So that's it. The only difference between the AIS and the LiDAR pipelines really is the implementation of PDAL to rasterize the points. So our final outputs will look something like this. And we might decide to rasterize the AIS points. But in this case, I just wanted to see how capable the GeoParquet would be. And GeoParquet is a vector-based format, so we wouldn't be able to rasterize those here. We would go to GeoTIFF for that. So overall, you can see what we have here through each of these frames is we have the NOAA Blue Topo bathymetry loaded as our base map, and we have the satellite imagery for the terrigenous portion of this map. And then we are loading on top of that the LiDAR data that we scraped from the USGS 3D elevation program. And we processed that for two main conditions. One is we've excluded anything that was higher elevation than 10 meters because we were interested in coastal overlap with the bathymetry. So everything less than 10 meters elevation is in the LiDAR. And if there is any topobathymetric data, we would keep it because we have also imposed a superseding condition where we take the highest classification available for any given meter and we take that as the data point. So that we're not necessarily averaging that you would normally do with a group by aggregation. We're just sorting and ranking. So for any given spatial footprint or any given meter in our digital elevation model, we have the highest classification available for that cell. Likewise, with the AIS data, we're doing the same logic, except instead of a LiDAR classification, we are using the maximum reported draft for a given cell, and the cell sizes are 45 meters in this case. And those were approximated by using the H3 Uber's H3 hexagonal system at the level of detail 11 gives you about 45 to 50 meter cell size. So we have 1 meter digital elevation model in the LiDAR data, 45 meter bins with maximum draft from the AIS data. And now we can see how all of these data sets play together. And by using the Uber H3 system with them, we're able to co-locate the AIS shipping traffic data to the LiDAR data and to the bathymetry, given that they all are potentially sharing the same Uber indexing or spatial indexing as H3 cell IDs.